we've looked at shear stresses in a few different cross sections. One more somewhat unique cross section I wanted to look at, just to make note of something, a few unique considerations, is the circular cross section. So one thing you'll remember, if you look back at the course notes, is that the shear formula is only applicable for planes that are perpendicular to the beam boundary. So in other words, if we're looking at a circle, we can use the shear formula right there at the neutral axis to find what the shear stress is on that plane. We can't use the shear formula. The shear formula is not applicable if we were to look at a plane up here and try to find shear stress at that plane, because the plane that we're looking at is not perpendicular to the boundary. See how there's an angle to it there, whereas the plane that we want to look at along the neutral axis is perpendicular to the boundary of the beam. You have a 90-degree angle between the neutral axis and the tangent of the circle there. So just wanted to make note of that, and then while we're here we can quickly calculate what the shear stress would be at the neutral axis if you have a circular cross section, and then this will come up in future chapters. So let's we'll note that this cross section, this plane that we're looking at, is along the neutral axis, and this circle we'll say has a radius of lowercase r. So if we want to calculate what the shear stress is along the neutral axis, we're going to use the typical shear formula, which is VQ over IT. So then we just need to determine what each of those things in the formula is. So let's come up to the other side here. We know that the problem says that the shear force is equal to F, so V, we can call that F. To get Q, if we're looking at the neutral axis, and we know that Q is going to be the area to either side of the neutral axis, which is going to be half of a circle. So you could look either at the top or the bottom. They're both half of a circle, right? So Q is going to be, and we're going to do this geometrically once again. So we're looking for the centroid of that shaded area, the location of the centroid of the shaded area multiplied by the area of that shaded area. So, and we won't derive what the centroid of that shaded area is. This is one you can just look up, and the centroid of the shaded area is 4r over 3 pi. And then the area of half of a circle is simply pi r squared divided by 2. And that's all going to simplify to 2r cubed divided by 3. Okay. We won't derive that here, but that is something you can look up or derive yourself. I is equal to pi r to the 4th divided by 4, and then T is equal to the diameter, so the width of the beam that we're looking at. So at that plane at the neutral axis, T is equal to 2 times r. Okay, so now all we do is plug each of those into the shear formula. So we'll end up with tau is equal to F times 2r cubed divided by 3, and that's all over pi r to the 4th over 4 multiplied by 2r, and we'll spare everyone the algebraic details, but that's going to be equal to 4 over 3 times F over pi r squared. Okay? So this is going to be the max shear stress in a beam with a circular cross section.